By way of introduction, let me just say that I'm talking about carbohydrate reduction in cancer. Now, this is much more speculative than everything we've been talking about. I think that we're all pretty much in agreement that the issue of carbohydrate reduction in improving features of metabolic syndrome and diabetes type 2 is an issue of science but politics. This is much more speculative, and so we're starting really at an earlier point here. But I'd like to talk about some perspectives that I have in it, hypotheses, some preliminary data, and let's see how we do. Oops, wrong one. Okay, first I'd like to thank my collaborators. About 9 years ago, I started as an adjunct with Richard at Downstate, and we were working on something else when he apologized to me because he got me interested in carbohydrate restriction, and no apologies needed. Okay, and we were interested in a number of other things, but the in vitro work has all been done at Downstate. With Richard's support, Anna Miller's been doing most of the work under guidance of Richard Ed Quadros in our lab across the hall, and Jeff Sequeira, who've really been tremendous assists to us. At Einstein, our clinical trial, which we just completed, I'll get to that as well, Joe Sperano is my oncology collaborator, CJ Isaacson, the lead nutritionist, and Sylvia Hertzkopf and Maria Romano have been nutritionists helping out there. I'll get this right. Funding has been through the Robin and Veronica Atkins Foundation, through the SUNY Research Foundation. Now, I'm going to be taking you on something of a whirlwind tour because the threads of this come from so many different areas that I hope I can kind of keep them woven and understandable. Right? But my day job is nuclear medicine. I mean, my background is internal medicine, and then I migrated into nuclear medicine. And in nuclear medicine, the 15-second lesson is that patients get mostly injected with the radioactive material, and it goes somewhere. And where it goes depends on its biochemical properties and blood flow. So it's a little different than X-rays. With X-rays, you're shooting an X-ray through someone, you get an outline of what's in the way. That's anatomy. In nuclear medicine, you're injecting something that has to get someplace by flow and get taken up by a particular mechanism. Okay, so that's really functional information as well as some anatomy. And a particular tracer that's become of interest in the last 10, 15 years is something called fluorodeoxyglucose. So you hear glucose is in the name. The fluorine happens to be fluorine 18, which is radioactive, so we can image it. Okay, and these are PET scans. PET scan has become essentially a one-step diagnostic metastatic workup because it allows you to visualize the fact that was observed by Otto Warburg almost 100 years ago that many aggressive cancers are glucose avid, glucose dependent. Okay? Now you can see here, this is a patient with metastatic colon cancer. Glucose is taken up in most of our organs. You can see a little heart. It's excreted in the kidneys, so you see the kidneys there in bladder because it's in the urine, a little urinary contamination here. You can see a little bit of the soft tissues. You can see the liver. But what you're not supposed to see are these big metastatic glucose-avid deposits in the liver. So this is metastatic colon cancer to the liver, showing up on a PET scan. This patient responded very well to chemotherapy, and you can see the follow-up scan shows a dramatic improvement. By the way, the heart can be quite variable. I mean, it shouldn't really be a surprise. It depends on what you ate beforehand. If you had a carbohydrate-rich meal right before the scan, you drive up insulin and it drives glucose right into your heart, and also fluorodeoxyglucose. So the heart uptake can be quite variable. Whereas this is an example of a treatment failure. I don't know how the contrast seems a little dark here, but I can't do much about it. Here you see the kidney, renal pelvis, where the FDG is excreted, the bladder, the heart again, quite variable. The liver, there's one metastasis right above the kidney, right there in the liver. On the follow-up study, I guess this is a little dark, but that met is there, but unfortunately so are several others. And there's also one in the lung. So this patient did not do well on chemotherapy. And so PET scans have become part of the toolkit that is used to diagnose and manage and follow patients who have cancer. Now, so my interest in cancer is I'm studying with Richard, and we're looking at low-carb diets in a variety of ways, the energetics, the metabolism. But I'm coming from nuclear medicine, where, in medical school I was fascinated with the Warburg effect, and PET scan's basis is basically that many cancers are glucose avid. And so, you know, at one point a bell goes off and I say, well, gee, I wonder if carbohydrate restriction may have any role in managing cancer. Now, we'll come back to that in a minute, because it's not quite as simple as it sounds. And many common aggressive cancers depend on glucose glycolysis particularly, okay? Most cancers of the lung, colon, breast, so major cancers, lymphomas, as well as many others of cervix, uterus, ovarian, melanoma, etc. But not all cancers are this avid for glucose. Prostate cancer, only about 20% of them show this kind of avidity. It's not that useful in prostate cancer. Certain kinds of colon cancer are not so avid, mucinous adenocarcinoma. Certain lung cancers are not that avid. Bronchoalveolar, very highly functional thyroid cancers are often not so glucose hungry. So the question is, why are some cancers, though, so glucose avid and so glucose dependent? So we have to sort of go back to what is cancer about? How does it arise? And where does it come from? So we need a little bit about normal tissue architecture and normal tissue physiology. Most of our cells in the body, normal cells, they line up like this. They're one layer thick. And they're very close to a capillary, which is supposed to be red cells, not ground cells. But anyway, with red cells in them. And there's a basement membrane, which all of our normal cells have an affinity for. They like to line up because there are signals that make it attractive to line up against the basement membrane. The basement membrane is on the lining of the vessel as well. There's connective tissue between them, but they're close. They're pretty close to each other. Now, what happens, I don't know, years ago I thought that cancer was something lurking in our body, that one cell becomes a cancer and then it takes a number of years before it finally manifests itself as large enough to be seen. That is not really, that may happen occasionally, I don't know how you can tell, but that's not generally what is thought to really occur. What's more likely to occur is that an abnormal cell develops. Not very abnormal, just a little abnormal. It loses its recognition of the basement membrane, so that cells can start to stack up. That's just called hyperplasia. It's not even an adenoma. It's not even called an adenomatous tumor. It's just called hyperplastic tissue. And sometimes they can stack up a little further. Now, the further you're away from the blood vessel, the greater the gradient is of nutrients and oxygen in the cells most distal from the blood vessel. And so the oxygen tension in the cells most distant from the blood vessel is lower. Hypoxia. Okay? I'm not showing you an adenoma. I'm showing you very regular distributions of cells. Now, hypoxia in the cells has consequences. The size of these benign tumors, of any benign tumor, is usually limited by regulatory mechanisms within our cells to try to prevent this from happening. Hypoxia, generally, induces something called reactive oxygen species formation within our cells. And they're not generally considered to be too good. They wreak chemical havoc inside cells. They cause proteins to malform. They cause genetic mutations. So reactive oxygen species may in fact be the final common pathway of cell damage, whether it's due to radiation or chemicals in the environment, but in fact, or hypoxia. So reactive oxygen species are not good. And in fact, our cells are taught, our cells have mechanisms within them to recognize reactive oxygen species, and the reaction is usually something called programmed cell death. The cell says, okay, this isn't any good, we're going to get mutations, we better stop, shut down. It's called apoptosis. And think of it as pruning. It's pruning the bad cells out. And it's a normal mechanism. Okay? So for a benign tumor to become much larger than what I showed you, something has to go wrong. Okay? Something further has to go wrong, not just the initial stacking of cells. So more adaptations have to occur. These are often mutations or other adaptations. So hypoxia, and I'm going to give you just one of them because there's really far too much detail in this talk, for which I apologize, but I don't know how else to get to the good stuff. Hypoxia is a key regulator in the production of increased reactive oxygen species because it induces something called hypoxia-inducible factor 1 alpha.